Dear students, today we are going to discuss about the three-phase inverter, and we are going to build a three-phase inverter in simulation. Okay, I have taken a black. So here I will take the power GY. Now I will take the source. So since it is an inverter, so your source will be, input source will be DC. Okay, so as earlier we have discussed that three-phase inverter required 6 switches, right? So we'll be taking 6 switches. So remember, you have to take a switch which is having diode. Okay, so press Ctrl R to rotate. Okay, fine. So now I am disabling this show measurement block. Okay, so your measurement block will not be there. Now I'm changing, I'm naming the switch as S1, okay, and S2, S3, S4, S5, S6. If you want copy paste, just click on right click and then drag. That's it. Okay. Okay. Now how to give the naming? Similarly in single phase how we have here. So upper will be the odd switches and lower will be the even switches, and just add 3 to this one. S1 plus 3 is equal to S4. Then S3 plus 3. And then S6. 5 plus 3, that is 8. Since only 6 switches are there, 8 minus 6 is equal to 2. So this is how we can able to. Sir, is it necessary to follow the same sequence? No, it is not required actually, but this is only for our purpose. I mean, it will be easy for us to follow this one. Okay, so for getting signals and all, it will not be make any confusion. Okay, so it is not mandatory. Okay, again I am telling you, it is not mandatory to follow all these steps. Okay, all this switches sequence, you can follow your own sequence also. Okay. Okay, so now each leg will be acting as a phase, one phase, A phase, B phase, C phase. Okay, A phase, B phase, C phase. Fine. Now I am changing this solver. Okay, before changing the solver, we'll try to change automatic to. So in this one it is asking like this. Okay, in case if it is going to ask, then you can change it. Okay, so discrete, and you can maintain 10. Okay. Okay. As much as your low is your sampling time, your response will be that much. It will be a very good response. Okay. In case in some digital applications, sampling time may not be supportive up to 10 microseconds. Then you can go for 20, 40, like that. Okay. Fine. So in general, since it is a three phase, a minimum voltage we are going to maintain is 600 voltage. Okay, in order to get a 415 voltage output. Okay, fine. Now I am using only a load. Okay, resistive load. Currently, I am not taking any inductive load. So, so here I am taking the RLC branch, not the load. Okay, already in last lecture I have told you what are the difference between the this load and the branch. Okay, so I try to take it in ohms. Okay, randomly I have taken. Fine. Now I'm going to connect in a star connection. Okay, star connection. This is for A phase, B phase, and C phase. Okay, now I want to connect the neutral to the ground. Okay, neutral to the ground. Fine. So now I want to calculate the voltage and current. Okay, here you can able to calculate the phase voltage and line voltage because it is a star connection. So you are going to have line voltage as well as a phase voltage. Whereas current, line voltage is equal to phase voltage because it is a star connection. Okay. So we'll try to measure both current and voltage so that we can able to calculate the power. Okay. Current, it has to be connected in series. Okay. So now voltage we can able to measure in two ways, right? So I will try to give tags. Okay, that will be easy. Signal routings I will give. Okay, so signal routings, and this is our current. Okay, current. So in last class, in last video we have discussed this global and local, right? Okay, so this is I. Simply I am taking I. Okay. Next, I am trying to calculate the voltage. If we are going to calculate the voltage across two phases, this is called line voltage. Okay, this is called line voltage. I will take it as VL. Okay, line voltage. We'll make it global. Okay, apply. Okay, fine. Now I want to calculate the phase voltage also. Okay, then how to calculate the phase voltage? You take one phase and another one to the neutral. Okay, another one to the neutral. Then I will take it as a V phase. Okay, phase voltage. Fine. Okay, what is the relation between line voltage and phase voltage? Line voltage is equal to root 3 times of phase voltage. Okay, so now what is the formula for the to calculate the power? So this is the power. Okay, power. In case if it is a phase voltage, then it is 3 into V phase I phase into cos theta. And in case if it is a line voltage, if we are going to consider, then it is root 3 into VL IL cos phi. Okay, fine. Now we will try to calculate the values also. Okay, fine. Till now what we have got, these are the actually line voltage, but it's not the RMS value. So we want to calculate the RMS value actually. Okay, so these are nothing but the RMS values. These are the RMS values. Okay, phase voltage, okay, phase current, line voltage and line current. Okay, so these are the RMS values. So for this one RMS value, we go here measurement block. In the measurement block, additional measurements you are going to see. So here you can see RMS. Okay, drag it and you can click on this one. Actually by default it will be 60. You convert them into the 50 and minimum, since it is a current, we just maintain it 10. Okay, apply. Then similarly here also you can apply RMS value. Initially let us say suppose 120. Okay, sampling time if you want to give, we can give 10 into e power minus 6. Okay, here also we'll give. Better you maintain sampling time everywhere the same value. Okay, otherwise it will ask also sometimes. Okay, this is the RMS value. Okay, we got all values RMS value. Fine. Now we want to give the uh, gating pulses. Okay, for this gating pulses we will use a sinusoidal pulse width modulation. Okay, we'll use a sinusoidal pulse width modulation. For that we need a sine signal. Okay, before going directly to there, first I want to check my sinusoidal signals. Okay, take one blank model. Okay, and then take sources, sine wave we have taken for change. So amplitude is okay. This is, since it is a radians, so it is, we have to 2 into pi into 50. This is our frequency which we are trying to maintain. Phase difference for phase A, we are taking it as a 0. Sampling time 10 into e power minus 6. Okay. Okay. So you take another one. So this is B phase. B phase is radians. So 120-degree phase shift is there. Okay. So what we can do actually here. Okay. So actually here we can observe that 180 is equal to pi, right? Pi. Then 120 is equal to how much? Okay. In such case, what we can have to say, that is 120 divided by 180 into pi. Okay. Will give minus value. Minus. Okay. Apply. Okay. Fine. Now same case here also. Instead of 120, we will take 240. Okay. 240. That's it. Apply. Okay. Fine. So now we will check it. Okay. We'll try to check it. So common use block. Use a mux one. Okay. How many inputs are there? 3 are there. Okay. So, sir, I don't want to. You can select all these 3. Press Control and select this one. Automatically, all this will done. Okay. Then use a scope. Place it here. Okay. Now I just want to check for, since it is a 50 Hz. Generally, what is the time period? It is 20 milliseconds. That is 0.02. I will take 0.04. 2 cycles. Okay. Run it. Fine. Now you can check. So we have got the exact 3 phases. Now I just wanted to check whether this blue color line is which exactly sine wave, which is it, this one or not. I just want to check it. Okay. So ensuring the results. Yeah. Okay. So it is perfect. So now I will take all these 3 signals. Okay. Control C. Is here. Okay. Now I will use these sine signals. Okay. I will use these sine signals to generate pulses for these switches. Okay. This is for the A phase, this is for the B phase, this is for the C phase. Fine. Now similar case, how we have done earlier, same case. Okay. We'll take one repeating sequence. We will take one repeating sequence. Sources. From sources you can go and take the repeating sequence. Now so here repeating sequence you can take. Similarly 0.25, then 0.5, 0.75, 1 divided by your frequency, whatever may be the frequency you want to choose. Okay, you want to run it. Okay, so this is the one. Then 1 0 minus 1 0. Fine. Apply. Okay. Now we need to relate it. No. So again go here. Use a relational operator. Okay, use a relation operator, and whenever our sine signal is greater than the repeating sequence, that is carrier signal, then it has to generate a pulse, right? That is our, I will try to zoom it. Okay, so this is our relation operator. Okay, now this is for the A phase. Okay, this is for the A phase. So signal routing, I will take signal. So this will be going to S1, right? So I will be taking this as, make it global. I will be taking it as a G1. Okay, G1. This is my G1. Okay. Now when this switch one S1 is conducting, S4 should not connect. Okay, S4 should not conduct. Otherwise, it will become a short circuit. Okay. So to avoid this one, what we are going to do? We are going to use a NOT. Same case. Earlier also we have done the same thing. So here we are going to take NOT. Apply. Okay. So now this is G1, then another one is G4. Okay, this is G4. Apply. That's it. Okay. Similarly, now you can able to do it for the remaining things also. Okay. Just copy this one, drag it, and place it. That's it. Okay, we'll see it. Okay. same repeating sequence you can take. Okay. Okay. However, you have to change the tags. You have to change the tags. This is for the B. B means this will be a G3. This will be G3. Okay. This will be G3 and this will be the G6. Okay. Apply. Okay. So now this will be the G5. Okay. This will be the G5. This will be the G2. G2. Apply. Okay. Fine. That's it. Okay. This is over. Now I want to check the results. Okay. This is completed. That is, our power circuit is over, our values are over. Still now we have not given actually the tax. Okay. We'll try to give the tax. Not given the tax. Okay. This is G5, G3, G6, G5. This is over. So now we have given the signals also. Okay. Now remaining thing is only to calculate and check the results. Okay. Fine. Now for this one, I will take a scope. Okay. I will try to take since see, we can able to give more number of things also, but problem is I would like to check this data. Okay. So this is VL. I will try to do individually. I will try to do individually. I will take only one port. Apply. Okay. This is a VL. Okay. This is a VL. Okay. So this is VL. Why I have taken, I will show you later. Okay. When we are going to do the THD analysis, then you will understand. Okay. This is for the phase voltage. I will change the name. Okay. Go to settings, logging data. This is V phase. Phase. Apply. Okay. So I want to check all the results at once. Okay. Till now we have not calculated actually the phase or the power and the power. Okay. So we will try to do it. So number of inputs 2. Okay. Apply again. Better will not take these things into logging data. Actually, why we have to take care of these things means it will take unnecessary memory. Okay, when we are not required, then why unnecessarily we have to send it to the workspace. Okay, now we have calculated the current, we have calculated the VL, line voltage and phase voltage, but till now we have not calculated the power. Okay, this is I, this is line voltage, this is phase voltage. Fine. Okay. So what is the formula? Formula is, in case line voltage is there, then root 3. Root 3 is 1.732. Okay. 1.732 into VL into IL. Here cos theta I am taking it as 1 because it is a resistive. Okay. Since it is a resistive, voltage and current are in phase, so I am taking it as a 0. Okay, that is 1. I'm sorry, 1. Okay. Okay, so now I will take a gain. Okay, this is 1.732. Root 3 is 1.732. Okay, and I am using a product. Okay, I am doing the product. Cos theta I have taken as 1. Okay, same thing. I can you do the same thing here also. Sorry, instead we can take it like this. But here in phase voltage, it is 3, not root 3. Okay, in phase voltage 3 it is. So we'll change it to 3. Okay, then again we'll do the product. Okay, we'll do the product. We'll check it. Okay, here actually I want to check whether power from line voltage and phase voltage are same or not. Okay, we'll see it. So till now everything is over. Fine. Now I want to run this only for 1 second. Okay, so this is my total. Okay, I will try to drag it here. Okay, so this is our power circuit and this is our control circuit. Okay, this is a control circuit and this is our power circuit. Okay, so this is a measurement block. Okay, this is our measurement. Fine, now we'll try to execute it. Now we'll check the line voltage. Okay, we have calculated the, we try to check the this result. Okay, so this is coming around 438. Okay, 438. So this is phase voltage. Okay, it is coming around 252. Now we'll see. Okay, this is our intention. No, yeah, you can check here. So the power is same. Okay, power is 1.92. 1.92. Okay, fine. Now I just want to check the, instead of here we'll try to give it here. Okay, because we want to check the waveform actually. Okay, so because so that I can able to calculate the exact values. Apart from this, we'll try to check the waveforms also. Okay, waveforms and the pulses. Okay? And the pulses also we'll try to check. Fine. Okay, so here it is 4. We'll take which and all the 4s are, so all 3 sinusoidal signals and repeating sequence. Okay, repeating sequence and all the 3 waveforms. Okay, that I will be giving here, and all the pulses I will try to take. That is G1, G3, G5. Now we'll execute it. So this is our line voltage. Okay, and this is our phase voltage. Okay, so now we'll try to find out the THD, FFT analysis, and then this is the line voltage. Line voltage starting we have to give. We'll try to do it at 0.5. Okay, number of cycles 5, and then 50. Okay, see here we have to check take the which voltage you want, because we have sent two data, right? One is line voltage and the one is phase voltage. Okay, currently I'm doing for the line voltage. Okay, so I would like to go up to 10,000. Okay, so display. So this is our THD and this is the maximum value. This is maximum value. It is V max. Again, you have to convert this into 502.3 divided by how much? Root 2. Okay, 1.414. Okay, this is your RMS value, 355. Okay, 355 is your RMS value. So here you can check now phase voltage. Okay, I will try to check for the phase voltage. Here you can see 289.5. Okay, 289.5. Again, this is the maximum value. Okay, that is 289.5 divided by 1.414. Okay, that is 204. Okay, 204 Vm by root 2. Okay, fine. This is our phase voltage. Okay, so now we'll try to see here. Okay, and this is, we'll try to see for the one cycle. Okay, we'll try to check for the one cycle. Okay, this is for one cycle. You can see here it is little complicated here. I will try to do this way. This is our signals. Okay, this is for the A phase, this is for the B phase, this is for the C phase. Okay, hope you have understood all these things. This is how we are going to simulate the three-phase inverter. Okay, saving, fine, save as. So three-phase SPWM. Okay, desktop. See here, you are going to get two formats, SLX and MDL. Whichever you want, you can able to do it. Okay, SLX means SLX or MDL. Okay, sir, I want to convert this into the lower version, sir. And then file, export model to. Okay, export model to previous version. Okay, previous versions. Whichever you want, you can able to do it. Okay, whichever the different version you want, you can able to do it here. Okay, that's it. Okay, you select it and you can save it. Okay, whichever format you want, SLX or MDL format. Okay, that you can select and you can have to save it. So this is about the three-phase inverter. Next class, in next videos, we are going to see the experiments. Okay, good luck, good night.